Welcome! In this session, we will delve into the problem number 74, search a 2D matrix. Together, we'll explore the problem statement, its challenges, and various approaches to solve it. Let's get started. In this problem, we are tasked with searching for a specific integer, called target, in a 2D matrix. The matrix has some special properties that we can use to simplify our search. First, within each row, the integers are sorted in ascending order from left to right. Second, the first integer of each row is greater than the last integer of the previous row. These properties essentially make the matrix behave like a sorted array when viewed row by row. Your job is to determine if the given target exists in the matrix. If it does, you return true, otherwise, you return false. The input consists of the matrix, which is a list of lists with m rows and n columns, and the target, which is the integer we are searching for. The output is a Boolean value indicating whether the target is found in the matrix. Let's look at the first example to understand this problem more clearly. Here, the matrix is a 3x4 grid with the rows and columns sorted as follows. The first row contains 1, 3, 5, 7, the second row contains 10, 11, 16, 20, and the third row contains 23, 30, 34, 60. The target we are searching for is the number 3. Since the matrix is sorted both row-wise and column-wise, we can see that 3 is present in the first row. Therefore, the output for this example is true. Breaking it down further, the rows of the matrix are as follows. Row 1 contains 1, 3, 5, 7, row 2 contains 10, 11, 16, 20, and row 3 contains 23, 30, 34, 60. Because the target is 3, we can confirm its presence in the first row. Now, let's consider another example. In this case, the matrix is the same, but the target is 13. Since 13 is not present in any of the rows, the output here is false. To elaborate on why the output is false for the second example, we can again examine the rows of the matrix. The integers in row 1 are 1, 3, 5, 7, row 2 contains 10, 11, 16, 20, and row 3 contains 23, 30, 34, 60. The target value of 13 does not appear in any of these rows, so the function correctly returns false. Now, let's consider a third example. Here, the matrix contains only 2 rows, the first row contains 1, and the second row contains 3. The target is 3, which is present in the second row. Therefore, the output in this case is true. Analyzing the third example further, the matrix is quite simple, with just 2 rows. Row 1 contains 1, and row 2 contains 3. Since the target is 3, and it can be found in the second row, the function returns true. Now, let's review the constraints and edge cases for this problem. The matrix can have up to 100 rows and 100 columns, so it's important to ensure that the solution is efficient. The values in the matrix and the target can range between -10⁻4 and 10⁻4, and the matrix always satisfies the given sorting properties. Let's also consider some special edge cases. The edge cases to watch out for include scenarios like a single row or a single column. For a matrix with only one row, the search should properly handle that row. Similarly, for a single column matrix, the search should work correctly as well. If the target is not present in the matrix at all, the function should return false. Additionally, the solution should handle extreme values, such as when the target is the smallest or largest possible value within the constraints. Finally, if the matrix is empty, meaning either m or n is 0, the function must immediately return false. These considerations ensure that the solution is robust and handles all possible inputs. To begin, let's consider the brute force approach. This method is straightforward. It involves iterating through every single element in the matrix to check if the target exists. While the matrix has specific properties, such as each row being sorted and the first element of each row being greater than the last element of the previous row, the brute force approach neglects these features. Instead, it treats the matrix as a generic 2D array. The algorithm for this approach is simple: traverse each row, and within each row, traverse each column, comparing each element to the target. If the target is found, we return true, otherwise, we return false after completing the traversal. However, this method is inefficient, as it requires checking every element individually, resulting in a time complexity of O, m*n, where m is the number of rows and n is the number of columns. The space complexity, on the other hand, is O(1), since no additional space is required. Despite its simplicity, this approach is not optimal for large matrices because it fails to take advantage of the matrix's sorted structure. A more efficient strategy is to perform binary search in each row. Since each row is sorted, we can take advantage of this property by applying binary search individually on every row. This significantly reduces the number of comparisons within each row. Here's how it works: we iterate over each row, and for each row, we perform a binary search to locate the target. If the target is found in any row, we return true. If we finish iterating through all the rows and the target is not found, we return false. The time complexity for this method is O(m*log n, where m is the number of rows and n is the number of columns, because binary search reduces the search space from n elements in a row to log n. The space complexity remains O(1), as we do not require additional data structures. However, this approach is still suboptimal because it fails to utilize the relationship between rows, specifically the fact that the first element of each row is greater than the last element of the previous row. While this is an improvement over brute force, it doesn't fully capitalize on the structure of the matrix. The most efficient and optimized approach treats the matrix as a flattened 1D sorted array. This approach leverages the matrix's properties, the sorted nature of each row and the sequential ordering of rows, to perform a single binary search across the entire matrix. The key insight here is to map any index in this hypothetical 1D array to the corresponding 2D index in the matrix. Using the formulas row equals mid / n and col equals mid %n, we can directly access the element at the mapped position. The algorithm involves performing binary search over the range from 0 to m*n1, where m is the number of rows and n is the number of columns. At each step, we compare the element at the mapped index with the target. If they match, we return true. If the element is smaller, we search the right half, and if it's larger, we search the left half. If the search completes without finding the target, we return false. This method achieves a time complexity of O(log m*n), as we are performing binary search over all the matrix elements, and the space complexity remains O(1). This approach is the most efficient because it fully utilizes the matrix's structure, minimizing both time complexity and space usage. By combining binary search with the matrix's properties, this strategy not only achieves the best performance but is also simple to implement, making it the clear choice for larger matrices. To solve the problem efficiently, we can treat the given 2D matrix as if it were a flattened 1D array. This approach allows us to leverage the sorted nature of the matrix while keeping its original 2D structure intact. The first step is to define our search space. If the matrix has m rows and n columns, the total number of elements is m*n. Conceptually, we treat this as a single sorted array of length m*n. Now, to map between the flattened array and the original 2D structure, we use the index k. Specifically, the element at index k in the 1D view corresponds to position k /n, k% in the 2D matrix. With this mapping in mind, we initialize two pointers, low and high, to represent the range of this 1D array. Initially, low is set to 0, and high is set to m*n1. Next, we perform binary search on this conceptual 1D array. At each step, we calculate the middle index, mid, using the formula low plus high /2. Then, we map mid back to the 2D matrix using the row and column calculations. The value at matrix, row, col, is then compared with the target. If it matches the target, we return true. If the value is smaller than the target, we narrow our search to the right half by updating low to mid +1. If the value at matrix, row, col, is greater than the target, we instead narrow the search to the left half by updating high to mid 1. This process continues until either the target is found or the search space is exhausted. If the loop terminates without finding the target, we return false. Now, why does binary search work well for this problem? The matrix's sorted properties allow us to treat it as a 1D array, enabling us to perform the search in logarithmic time, which is significantly more efficient than a brute force approach. The mapping formula, row equals mid /n, col equals mid %n, is key to translating the flattened index back to the 2D structure. Additionally, the algorithm handles edge cases effectively. For example, if the matrix is empty, meaning m equals 0 or n equals 0, the function immediately returns false. Similarly, if the target is smaller than the smallest element or larger than the largest element in the matrix, the algorithm gracefully terminates without unnecessary computations. This efficiency is achieved without creating any additional data structures, as the input matrix is accessed directly, and the search is managed using simple pointer variables, low, high, and mid. The algorithm's key operations further highlight its efficiency. First, instead of creating a new 1D array, we directly map between the 2D and 1D indices. This saves memory while still enabling binary search. Second, the binary search algorithm itself ensures that the search space is halved at each step, leading to an impressive logarithmic time complexity. Speaking of complexity, the time complexity of this approach is O log m*n, where m*n represents the total number of elements in the matrix. This is because the binary search operates over the entire conceptual 1D array. The space complexity is O(1), since no additional data structures are used, and only a few simple variables are required. Let's consider an example to make this more concrete. Suppose the input matrix is as follows: 1, 3, 5, 7, 9, 11, 13, 15, 17. This matrix has 3 rows and 3 columns, giving us a total of 9 elements. The algorithm will treat these elements as a single sorted sequence, and will search for the target value within this conceptual array. By mapping indices correctly, we avoid the need to explicitly flatten the matrix. Now, let's walk through the execution step by step with a target value of 9. First, we initialize our pointers, low equals 0 and high equals 8, since there are 9 elements in total. Next, we calculate mid as 0 plus 8, // 2 equals 4. Using the mapping formula, we translate this to position 1, 1 in the matrix. The value at matrix 1, 1 is 9. Since this matches our target, the algorithm returns true, successfully finding the target in the matrix. As for edge cases, consider an empty matrix or a target value that's outside the range of the matrix's elements. For an empty matrix, the algorithm quickly identifies that there are no elements to search and returns false. Similarly, if the target is, say, 20 greater than the largest element, the algorithm terminates efficiently due to its boundary checks. These examples illustrate the algorithm's robustness and ability to handle diverse scenarios while maintaining optimal time and space complexity. This solution efficiently searches for an element in a 2D matrix using binary search. First, we check if the matrix or its first row is empty, returning false immediately in such cases. The number of rows and columns is determined, and we define a search range with left set to 0 and right set to rows *calls 1. The matrix is conceptually treated as a 1D array for binary search, with the middle index mid computed as left plus right, // 2. The matrix's 2D indices are derived using mid // calls for the row and mid % calls for the column. The value at this position, mid_val, is compared to the target. If mid_val matches the target, we return true. If min_val is less than the target, we adjust the left boundary to mid plus 1. Otherwise, we adjust the right boundary to mid 1. The loop continues until left exceeds right, at which point the target is not found, and we return false. This approach ensures logarithmic time complexity, O log m*n, making it highly efficient for sorted 2D matrices. This is the Java implementation for LeetCode problem number 74, search a 2D matrix. The logic mirrors the Python version, employing binary search to treat the 2D matrix as a flattened 1D array. Key differences include type declarations and Java's class structure. The algorithm efficiently searches the matrix using O log m*n complexity, where m and n are the matrix's dimensions. To solve the problem of searching in a 2D matrix, we treat the matrix as if it's a flattened 1D array. First, we initialize rows and calls to capture the matrix dimensions, which are 3 rows and 4 columns in this case. This gives us a total of 12 elements, so we set left equals 0 and right equals 11 to represent the start and end indices of this virtual 1D array. In the first iteration, we calculate the midpoint as mid equals 0 plus 11 // 2 equals 5. To access the value at this midpoint in the 2D matrix, we compute mid_val equals matrix 5/4 5% 4 equals matrix 1 1 equals 11. Since 11 is greater than the target value of 3, we narrow our search range by updating right equals mid 1 equals 4, effectively discarding the right half of the search space. With the updated search range, we proceed to the second iteration. The new midpoint is calculated as mid equals 0 plus 4 /2 equals 2, and the corresponding value in the matrix is mid_val equals matrix 2 /4 2% 4 equals matrix 0 2 equals 5. Since 5 is still greater than the target value of 3, we again adjust our range by setting right equals mid 1 equals 1. In the third iteration, the midpoint is recalculated as mid equals 0 plus 1 /2 equals 0. The value at this position is mid_val equals matrix 0 /4 0% 4 equals matrix 0 0 equals 1, which is less than the target. This time, we update left equals mid plus 1 equals 1 to narrow the range to the right. Finally, in the fourth iteration, we find mid equals 1 plus 1 /2 equals 1, and the value at this position is mid_val equals matrix 1 /4 1% 4 equals matrix 0 1 equals 3. This matches the target, so we return true, confirming that the target is present in the matrix. Now, in the second example, we check for a target value that is not in the matrix. Again, we initialize rows equals 3, cols equals 4, left equals 0, and right equals 11. In the first iteration, we calculate mid equals 0 plus 11 /2 equals 5, and the value at this position is mid_val equals matrix 5 /4 5% 4 equals matrix 1 1 equals 11. Since 11 is less than the target of 13, we adjust our range by setting left equals mid plus 1 equals 6. In the second iteration, we find mid equals 6 plus 11 /2 equals 8, and the value is mid_val equals matrix 8 /4 8% 4 equals matrix 2 0 equals 23. This time, 23 is greater than the target, so we update right equals mid 1 equals 7. In the third iteration, the midpoint becomes mid equals 6 plus 7 /2 equals 6, and the value at this position is mid_val equals matrix 6 /4 6% 4 equals matrix 1 2 equals 16. Since 16 is also greater than 13, we narrow the range further by setting right equals mid 1 equals 5. At this point, we reach the exit condition where left equals 6 is greater than right equals 5. This indicates that the target value is not present in the matrix, so we return false. Lastly, let's consider the edge case where the input matrix is empty. Since there are no elements to search, we immediately return false without performing any further computations. This ensures that our solution handles all possible input scenarios effectively and efficiently. To analyze the time complexity of our algorithm, let's start by understanding the binary search approach in the context of a 2D matrix. First, the matrix is conceptually treated as a flattened 1D array. Accessing any element in the matrix using the formula matrix, mid /4 cols, mid% cols, takes constant time, 1, because it's a straightforward index calculation. Now, binary search operates on the total number of elements in the matrix, which is rows * cols. In each iteration of the binary search, the search space is halved, and this halving continues until the search space is reduced to one element. The number of iterations required for this process is proportional to the logarithm base 2 of the total number of elements. Therefore, the time complexity of the binary search is O log rows * cols. To make it simpler, if we let n represent the total number of elements in the matrix, the time complexity is expressed as O log n. This is a significant improvement compared to a naive approach of linear search, which would require O n time. Now let's shift our focus to the space complexity of the algorithm. The algorithm is highly space efficient and operates in constant space. The input matrix and the target value are given directly as inputs, so they do not contribute to additional space usage. During the binary search, 3 integer variables left, right, and mid are used to define and update the search boundaries. Additionally, we use a single integer variable mid_val, to store the value of the matrix element at the current midpoint. Since no other data structures are used and the number of variables remains constant regardless of the input size, the space complexity is O(1). When we consider the best, average, and worst-case scenarios, the time complexity remains consistent. In the best case, the target is located in the first iteration, which takes O(1) time. On average, the algorithm performs a logarithmic number of iterations, leading to O log n time complexity. In the worst case, the target is absent from the matrix, and the binary search exhausts all possible search space, which still results in O log n time complexity. Let's compare the optimized binary search approach to a naive solution. In a naive approach, we would iterate through every element in the matrix sequentially to find the target. This would require O(n) time, where n is the total number of elements in the matrix, calculated as rows asterisk calls. In contrast, the optimized binary search approach significantly reduces the time complexity to O log n. This improvement is achieved by leveraging the sorted property of the matrix. By having the search space in each iteration and directly accessing elements using efficient index calculations, binary search avoids the need to check every element. Mathematically, the binary search process works by dividing the search space by 2 at each step. Starting with n elements, it takes log 2, n iterations to reduce the search space to a single element. Since each iteration involves only constant time operations, such as index calculations and comparisons, the overall time complexity is O log n. Moreover, the space complexity remains O(1), because the algorithm operates in place without using additional data structures. This combination of logarithmic time complexity and constant space usage makes the binary search approach a highly efficient solution for searching in a 2D matrix. When working with this problem, there are some common mistakes to watch out for. First, many people confuse row and column properties of the matrix. The matrix is sorted row-wise and column-wise, but that doesn't mean the entire matrix is globally sorted. Misunderstanding this can lead to incorrect traversal strategies that either miss the target or take unnecessary steps. Next, relying on a brute force search is another frequent issue. If you iterate through every element without leveraging the matrix's sorted structure, you'll end up with an O(n)(m) time complexity, which is far from optimal. Finally, be cautious of off-by-one errors, especially when initializing pointers for binary search or managing boundary conditions. These errors can lead to runtime issues or incorrect outputs, so it's crucial to handle indexing carefully. Now, let's think about other pitfalls. One major issue is not handling edge cases properly. For example, what happens if the matrix is empty, or if it only contains a single row or a single column? Similarly, scenarios where the target value is smaller than the smallest element in the matrix or larger than the largest element are often overlooked. Ignoring these edge cases can cause your algorithm to fail or produce incorrect results. Another point to consider is inefficient space usage. Some solutions convert the 2D matrix into a flat array, which increases space complexity unnecessarily. While this may simplify the implementation, it doesn't meet the problem's constraints for in-place solutions, and interviewers are likely to prefer algorithms that are both space and time efficient. To excel in interviews, it's important to focus on key insights about this problem. Most interviewers expect you to take advantage of the sorted nature of the matrix, so brute force solutions should be avoided. Instead, aim for optimized approaches like binary search or the stair-step method. Clearly explaining how you handle edge cases and boundary conditions is also critical. This shows that you've thought through potential pitfalls and ensures your solution is robust. Another important aspect is how you use comparisons to guide your traversal, whether it's comparing the target with the current matrix element or determining whether to move left, right, up, or down. Additionally, be ready to discuss trade-offs between approaches like binary search and stair-step search. Explaining their complexities and when each is appropriate demonstrates a deep understanding. Finally, recognize that many matrix problems involve reducing the problem space efficiently. Practice identifying when the sorted properties of the matrix can simplify your solution. Related problems, like LeetCode 240 or LeetCode 378, are great for building this intuition. There are also several alternative approaches worth considering, each with its own trade-offs. The stair-step search is a straightforward method where you start at the top right corner of the matrix and move left or down based on comparisons. It runs in O, n plus m, time and uses O1 space, making it simple to implement, though it doesn't exploit binary search. Another approach is binary search across the rows, treating the matrix as a flattened 1D array and mapping indices back to 2D coordinates. This is highly efficient at O log n asterisk m, time and O1 space, but it can be harder to implement and debug due to the complexity of index mapping. Lastly, there's the divide and conquer approach, which breaks the matrix into quadrants and recursively searches only the relevant regions. While elegant, this method is less intuitive and has a higher complexity of O, n asterisk log m or O, m asterisk log n time, depending on the dimensions. Each of these methods offers unique advantages and challenges, so understanding when to apply them is key. Great work! We reviewed the problem, search a 2D matrix, and discussed key insights. Remember, starting simple and optimizing is a great way to tackle coding problems. Keep practicing, and stay motivated. See you next time. That's the end of this tutorial. I hope you found this explanation helpful for understanding the solution to this LeetCode problem. If you enjoyed this content, please consider subscribing to the channel for more coding tutorials and solutions. Feel free to leave a like if this video helped you, and don't hesitate to comment with any questions you might have. Thanks for watching, and happy coding!